So we have this question. It says that C01 be the Banach space of real valued continuous function on closed interval 01 equipped with supremum norm. And we have defined T such that T of fx is equals to integral 0 to x ftdt. Let RT denote the range space of T. Consider the following statement. The statements are: T is a bounded linear operator. T inverses Bt to C01 exists and is bounded. Then we have to check that which of the statement is true. P is true, Q is true, or both are false. So we have to check this, right? So first of all, we know that if I have to check boundedness, I have to check that norm of Tf should less than equals to K norm of F. Then I'll say that T is bounded for all F. If this condition holds, then I'll say that T is bounded. Now, how can I prove T inverse is inbound? T inverse is bounded, right? For T inverse bound, uh, from this I'll get T is bounded, because if T inverse exists, let's suppose T inverse exists, if I'll prove norm of Tf greater than equal to K norm of F for every F, then I'll get that T inverse is bounded, right? Because what will we get if we'll take this T to the right side? So I'll get T inverse is bounded, right? If I'll get lower bound for T, that means T inverse has a upper bound, right? So we have this. So using these two formulas, we'll check that either T is bounded or T inverse is bounded, right? So let's start with our T. So we have given here, if I'll see, T is given to us that T of fx 0 to x integral ftdt, right? So can I start finding norm of Tf, right? That's what I have to do here, norm of Tf. So that would become norm of 0 to x ft dt. That would be my integral. So can I take this x outside, because it's not doing anything here, and because we have integral over T. So norm will be supremum of x belongings to 0 comma 1, because they have given that we have to take supremum norm, right? 0 comma 1, and because the interval here is 0 comma 1, right? So it will become x integral 0 to x ft dt. This will be my formula, because now x belongs to 0 comma 1. So that means if I multiply it with this, for x is equals to 1, I'll get the maximum value. So I can write down it equals to supremum of x belongs to 0 comma 1, and it is modulus of integral 0 to x ft dt, right? Now, can I write this equals to supremum norm of f? Because ft is integral over 0 to x ft dt. So, can I write down this norm of ft? Because norm of ft is maximum, or I can write norm of f. Right? There is no use of t because I have taken it outside. So, I'll write down here norm of f, and it will become 0 to x integral dt, and we have to take supremum over this 0 to x. Now if I'll integrate this, I'll get x. Supremum of x will be x belongs to 0 comma 1, that would be 1. So I'll get here 1 into norm of f. So that means I'll get one case such that for all f, t of f is less than equal to, so I can write here norm of tf is less than equal to 1 into norm of f. So I can say that here T is bounded, right? So that means statement P is true. T is a bounded linear operator. But now I have to check it for Q. So first of all, I have to check T inverse exists. If it exists, then I have to check that it is bounded or not. Now for existence, because if when will T inverse exist? T inverse will exist when T is 1 1, right? T inverse exists when T is 1 1. So let's check T is 1 1 or not. So what would I take? I'll take T of F1 is equals to T of F2, right? So that would become 0 to x F1t dt equals to 0 to x F2t dt, right? I'll take this integral x and x will get cancelled, and if you will solve this, you will get, because you will get 0 to x f1 in 0 to x f2 integration. So that would give you f1 is equals to f2. Now t is 1 1, t is 1 1. So that means T inverse exists, right? We get two condition that T is 1 1. Now T inverse exists. Now I'll move down to uh, proving this, checking this, that if it exists, then T inverse is bounded, right? So let's start to check here that this condition hold or not. Let's take one example here. So if I'll take f is equals to x to the power n, let's take f is equals to x to the power n on closed interval 0 comma 1, right? If I'll take this, what would be norm of f? Norm of f, supremum of x to the power n on 0 comma 1, that would be supremum of x to the power n on closed interval 0 comma 1, right? So I'll get 1, that would be my supremum. Norm of f is 1. Now I'll find out norm of tf. Norm of tf is equals to supremum integral 0 to x to the power n dt, right? T to the power n, that would become, because ft is t to the power n. Okay, so that would be t to the power n. Now I'll integrate this. If I'll integrate t to the power n upon n plus 1, so I'll get x to the power n plus 1 upon n plus 1, and I have here supremum. Now for supremum x belonging to 0 comma 1, maxima will occur at x is equals to 1, so I'll get the norm of tf is equals to 1 upon n plus 1. Now if I'll check this condition says that norm of tf should be greater than equal to k norm of f, right? Let's put the value, so I'll get k greater than equal to 1 upon n plus 1. So is it possible for any k? Let's suppose if I'll take any k greater than 0, it is not possible always. So I can say that T inverse is not bounded. T inverse is not bounded, right? Why it's not true? Because if I'll take k is equals to 1 upon n plus 2, then it would not be true. So that means for this case, I get that t for one, I get one f such that t of f is not greater than equals to k norm of f. So I can say that T inverse is not bounded. So that means P statement is true, but Q statement is false. This statement is false. So option B is my correct answer. Right here, option B is correct. And why we got that? Because it's not possible.